So this is just a general introduction to the idea of free energy. If you looked at the introduction to entropy, you know that one of the really fundamental principles of physics is that everything that happens in the universe is accompanied by an increase in the entropy of the universe as a whole. But that doesn't necessarily mean that in the local system we're looking at, so what's happening in the test tube or whatever, it doesn't necessarily mean that the entropy change there is either positive or negative, because the enthalpy change, the heat given out or taken in, also affects the entropy of the universe. And so the local entropy change can be either positive or negative. So what would be nice would be to have a way of calculating what the overall entropy of the universe, or the change in that, would be, so that we would know whether a given process would be feasible or not. And that sounds incredibly challenging, but actually there is a surprisingly simple function which you can work with, which tells you that, and that's what the free energy is. So the free energy, which is G for short after Gibbs, who was the person who devised this term, it's defined as G is equal to H minus Ts, where H is the enthalpy and S is the entropy. But for our purposes, we're essentially always going to think about the change in these functions rather than their absolute value. So we're sort of going to define it much more usefully like this, as delta G is equal to delta H minus T delta S, where we're effectively saying, right, we're working at a constant temperature, so T is whatever it is, it's a constant value, and we just plug in these values. So that is the definition of free energy. And the thing that's important about it is that if delta G works out to be negative, that corresponds to an increase in the overall entropy of the universe, so that's a feasible process. If delta G turns out to be positive, that tells you that the overall change in entropy in the universe would be negative, and therefore the process is not feasible, it's just not going to happen. So the entropy in the universe stuff you don't need to know about. All you need to know is, first of all, that definition, and secondly, the important feature of it, which is that if delta G is positive, a process is not feasible. So any reaction or physical change, anything at all that you might imagine happening, if you calculate delta G for it and it comes out to be a positive number, it means it cannot happen. Not at that temperature. But of course, as you can see from the definition, if you change the temperature, that conclusion may be different. On the other hand, if delta G is negative, then a process is feasible. And feasible is a word we've used before when we were doing electrochemistry, where we used electrode potentials to do a rather similar thing to predict whether a reaction could happen or not. We said feasible means that it could in principle happen, but it doesn't tell you anything about how quickly it happens. So a process may have a negative delta G and not appear to happen at all because its rate could be so slow if it has a really high activation energy. So remember, feasible means it could happen, not that it necessarily will. So those two things are the crucial starting point for everything to do with delta G. So learn the definition and learn the significance of the sign of delta G. The next thing is that you need to be able to calculate it from delta H and delta S. And here, in principle, that's just substituting numbers into the equation, so it shouldn't be hard, but you have to be really careful about units. So let's just look at that. So we write down our definition again. And you know that delta H is in kilojoules per mole, because you're very used to that from all the enthalpy work that you've done. And you can see that if delta G is just delta H minus something, then the units of delta G must be the same as delta H, because you can't just subtract something and change the units. So because delta H is in kilojoules per mole, so too is delta G. So that's the first thing, that you now know what the units of the free energy change are. But it's these terms where you've got to be really careful. Now T is the absolute temperature, which means that it's in Kelvin, not degrees C. And of course you know what the examiners are going to do. They're going to give you the temperature in degrees C normally, so you have to remember to convert it into Kelvin. And you know how to do that because you've done that a lot in ideal gas equation questions. So remember that that's equal to degrees C plus 273. So you have to remember to do that. And delta S is usually given in joules per Kelvin per mole, as you know from the stuff you've already done. But for this equation, it needs to be in kilojoules per Kelvin per mole, because the units have got to be compatible, and because we're working with kilojoules here and here, it needs to be kilojoules there as well. So that means that usually you have to take the number you're given in joules per Kelvin per mole and convert it. So that's joules per Kelvin per mole divided by 1000. Okay, so let's just look at a couple of examples of using that equation. So first we've got this one, we've got delta H, temperature, and delta S. So the first thing, as we said, is we've got to get the units right. So delta H is fine, but T has got to be in Kelvin. So we add 273, which turns that into 283 Kelvin. And delta S has got to be in kilojoules per Kelvin per mole. To go from joules to kilojoules, you divide by 1000. So that goes to plus 0.110 kilojoules per Kelvin per mole. Oops. Notice that throughout here we're using explicit signs for delta H and delta S. It doesn't matter that plus 40 in everyday life would just be called 40 and plus 110 would be 110. Remember that with everything in chemistry that could be negative, so delta H, delta S, electrode potentials, you always put explicit signs in, so it must either be plus or minus, not just a number. So we're doing that here, so we've got plus 0.110, and then we just plug them into the definition. So delta H is equal to delta H, so delta G is equal to delta H minus T delta S, which is equal to plus 40 minus 283 times 0.110, which is plus 8.9 kilojoules per mole. So that's the number. And then you've got to answer the question, which is it feasible? So you've got to explain what that number means. So don't just say, this means it's not feasible, because you haven't then stated explicitly what is it about that number. You know, like, is it because it's less than 97 that it's not feasible? And obviously the answer is that's not the reason. So you have to say explicitly, this is positive, and that means that the reaction is not feasible. So make sure you make the reasoning clear. This is positive, which means that the reaction is not not feasible. Okay, so we can do the same for this one. Now this one's going to be a little bit trickier because of signs, and one of the biggest problems with free energy calculations is people are sometimes a bit sloppy about the signs, so make sure you follow this carefully. So we do the same as before. We turn the temperature into Kelvin, so it's minus 40, so it's minus 40 plus 273, which is 233 Kelvin. Okay, so again, be careful about the signs, you don't just add 40, it's minus 40 plus 273. And with delta S, we have minus 90 joules, so we divide by 1000 and we get minus 0.090 kilojoules per Kelvin per mole. Okay, so that's straightforward enough so far. Now we come to substitute them in here again. So we get delta G is equal to delta H is minus 200 And then we have to be careful about the signs. So it's, if we just put in the numbers to start with, it's minus 233 times, and delta S is negative, times minus 0.090. And where you have to be very careful is that you're subtracting something negative here. So you either have to be really careful on your calculator, make sure you get the signs in accurately, or, because I'm old, I would probably not do it like that. I would probably say, right, you're subtracting something negative, and minus of a minus is a plus. So you could write it as minus 200 plus 233 times 0.090. Okay, so that's up to you. You don't have to write it in like that. You could just do that carefully on your calculator. But if you and your calculator don't always see eye to eye on things, then it may be better to just say, right, I'm subtracting a negative number, and that's the same as adding a positive number. Okay, so now it's straightforward. So minus 200 plus 233 times 0.09 comes to minus 179 kilojoules per mole. So this time it's negative. Okay, so you say delta G is negative, which means that the reaction is feasible. Okay, so what they'll sometimes do, of course, is make you do problems in which this needs rearranging to solve for either delta H or T or delta S. So let's just look at an example of that. So the first job this time is going to be starting with the usual definition, delta G equals delta H minus T delta S. We have to rearrange it to solve for delta S. So always, in this, as in everything else, rearrange the expression algebraically first and then put the numbers in. That's really important. You're more likely to get it right that way, but also you're much more likely to get marks for working if you mess it up, if you do it that way than rather than if you plunge straight in with the numbers. So we can, it depends how good your algebra is, you may be able to do that in your head, but if you can't, just do it one step at a time. If we add T delta S to each side, we get delta H plus T delta S is equal to delta H, and then if we subtract delta G from each side, we get T delta S is equal to delta H minus delta G, and then if we divide both sides by T, we get delta S is equal to delta H minus delta G over T. Okay, so that's going to be the expression we want to use. So be careful with those rearrangements. Again, don't be overconfident and do it in your head if you're not confident with your algebra. Do it one step at a time like that, and that's what you end up with. So now we can plug the numbers in. So delta H is minus 90, so we have minus 90, and then it's minus delta G, so it's minus 70. So again, being careful with the signs because you're subtracting a negative number there. So it's minus 90 minus 70 over T, 150 degrees C, but remember that has to go into Kelvin, so we add 273, which is 423 Kelvin. Okay, so we get 423 on the bottom. And again, you can either enter that directly into your calculator if you're careful, or you can say minus minus is a plus, so that's minus 90 plus 70 over 423, which works out as minus 0.0473. And you've got to remember to be very careful about the units, because we've been working with kilojoules here. The answer is going to be in kilojoules per Kelvin per mole, because that was what our input numbers were in, kilojoules per mole. So to turn that into joules, we've got to multiply by 1,000. So kilojoules to joules, you've got to multiply by 1,000. So multiply that by 1,000, you get minus 47.3, or two significant figures, since our data were two significant figures. So minus 47 joules per Kelvin per mole. Okay, so not difficult, but very easy to slip up on, particularly with the signs or forgetting to change the units of the temperature or whatever. So it's important to practice a lot of these questions.